Okay, let's talk about why ortho-para directors are ortho-para directors and basically generally activating, and then why meta-directors are actually meta-directors and why those are generally deactivating. All right? So remember when we talk about this term activating, that means that this reaction will proceed faster than benzene by itself, right? Which means that our intermediates are going to be more stable. Our intermediates are stabilized in relation to the intermediates of benzene. And then when a group is deactivating, that will react slower than benzene. So when you don't have a substituent group, and that the intermediates with the meta-directors are going to be less stable than those of benzene. All right? So what we're going to do is talk about two different examples. We'll look at two ortho-para directors and then one meta-director. So the first example we're going to look at is toluene. All right. So with toluene, we're going to be adding some generic E+. Okay, so this could be any reaction. It could be a chlorination. It could be a nitration. We'll just call this a general E+. And we're basically going to be adding this E+ to the para position, the ortho position, and the meta position, but really focusing on our intermediates here. Okay, because those intermediates are going to tell us where or how this is stabilized or destabilized and how it works. So we have our para group or ortho substitution and our meta substitution. So let's look at para. So if we take this alkene here and attack that E+, we will get this intermediate, right? We can draw a few resonance structures. So I can move this double bond here to here to get the next resonance structure. And then we can move the double bond from there to there to get our third resonance structure. All right. If we attack at the ortho position, we would attack using this double bond, Re+, right, which generates that carbocation here. And then we can draw two more resonance structures. We can move this double bond here to get this carbocation, and then move that double bond there to get that carbocation. Okay, and we know, we should remember when we have a methyl group here that we are going to get the ortho and para products. Right, so there's something about these intermediates here and here that's going to be better than the meta intermediates. Okay, let's look at the arrows for meta. So if we add meta, again, we'll take this arrow here, but we'll put the E on that position, generating a carbocation there. Right, and then we can draw our resonance structures, move our double bond to get a carbocation there, move our double bond to get a carbocation there. All right, so there is something about the intermediates, the carbocations formed when we attack para or when we attack ortho, that's better than the meta. So let's take a look at these carbocation intermediates. So what we're going to do is if we look at our first intermediate, we can see that this is a secondary allylic carbocation. The one in the middle is a tertiary allylic carbocation, and then the one at the right is a secondary allylic carbocation. If we look next here, that's a tertiary allylic, a secondary allylic, and a secondary allylic. And then if we look at the meta positions, we have a secondary allylic, a secondary allylic, and a secondary allylic. So what we can easily see here is when you attack and add at the para position, one of your resonance structures is tertiary. When you attack at the ortho position, one of your resonance structures is tertiary. But when you do at the meta, they are all secondary. All right. So because of these resonance structures, because we're forming the tertiary derivatives, right, because we have that methyl group there, that makes these two pathways here, sort of the para and the ortho position, more stable. right? Our intermediates here are going to be more stable. They're lower in energy as compared to the meta, right? Because the meta has 3 secondaries. So that's why for toluene, we see our major products are going to be the products where we add our electrophile at the para or the ortho position, right? And again, if we just take a look at benzene by itself, okay, so here we're starting with benzene. We're doing the same exercise here, right? We attack our E plus, right? Because there's no other group here, we can put our E plus wherever we want. And we see with our benzene derivative, we get a secondary allylic, another secondary allylic, right? And then a third secondary allylic. So we only get secondary allylic intermediates. So that's why when you have alkyl groups here, these are stabilizing, right? Because this tertiary structures that you get here are more stable than benzene and more stable than the meta position. All right, that's our first example for toluene. Let's look at another ortho para director. Let's look at phenol. Okay, let's look at phenol. Now we have an oxygen that has 2 lone pairs attached to it. So we know that this is going to end up being a ortho para director. There's our para position, there's our ortho position, and there's our meta position. If we go through the same exercise again, oops, and let's just correct this here. This should be OH, OH, and OH, right? So if we attack with this double bond and add our E at the para position, we get that carbocation. We can draw a resonance structure here to get this carbocation. And now there's 2 more resonance structures we can draw. So we can move the double bond here to get this. Or you can take the lone pair on the O, bring that down, and that gets you this resonance structure here. So you'll see in this example, we don't have 3 resonance structures, we actually have a 4th resonance structure. Let's look at when we add this E plus to the ortho. So if we attack here, we get our carbocation. We can move our double bond here to get our next carbocation. We can move our double bond here to get our next carbocation. But again, because this oxygen has a lone pair here, that lone pair can come down, right, to form, again, our 4th resonance structure here. When you attack at the meta position, so if we attack here, we get a carbocation there. Again, we draw our resonance. We see that we only have 3 resonance structures. Because the positive charge is never on the carbon connected to the O, we cannot draw a 4th resonance structure, right? And one thing we want to remember, the more resonance structures we have, the more electron delocalization, the more we're lowering the energy of this intermediate. So we now have the positive charge shared, right? Our positive charge is shared between that atom, that carbon atom, and the oxygen, right? So by having a 4th resonance structure, we have clearly stabilized the pathway where we add our electrophile to the ortho and their para position, and that does not happen with meta. So again, because we stabilize our intermediate, right? We stabilize our intermediate, that means that these are activators, right? And if you remember about phenol, this is a strong activator. So having this extra resonance structure really helps to stabilize this intermediate much more than just having a single tertiary, right? Toluene was slightly activating. Phenol is strongly activating. Okay, so next let's take a look at our meta directors. Let's try to figure out why a meta director is a meta director. Okay. Let's draw our arrows in. So here we know we have a ketone. We know that's a meta director. So this will be our major product meta. We could also possibly form the para or the ortho. So let's draw our arrows in. Right, if that double bond attacks, we get a plus. We can draw the resonance structure here, move the arrows, draw our third resonance structure. For the para attack, we could attack here and then put the E there, giving us a plus. Draw our resonance structure here, draw our other resonance structure there. Or if we attack at the ortho position, we could attack here to put our plus there. Sorry, let's erase these. I think my double bonds are in the wrong spot. Oh no, I just attacked from the wrong spot. There we go. Oh no, my double bonds are in the wrong spot. So we really, our double bond should be here, here, and here. So if you attack here, you would get a plus there, right? If we move our double bonds from here to here, we get a plus there. We move the double bonds, we get a plus here. So when I attacked it, when my arrows, my original arrows here would be attacking on the left side, all right? So what is special about this that's better? What's special about the intermediate when the carbocation intermediate when you have meta versus when you have ortho or para, all right? So to understand this, we really need to look at our carbonyl. And what's important to know with a carbonyl is you have a very, very strong dipole. And what that means is the carbon connected to the benzene has a strong partial plus and the oxygen has a strong partial negative, all right? So we can draw a partial plus on all of these carbons. As shown, okay? So the first thing we should notice is, let's talk up first why meta-directors are generally deactivating, why they're slower than benzene. And that's pretty simple. That's because the molecule has this partial plus charge. Every single one of these intermediates have a partial plus. So when we do our EAS reaction, we're generating a full positive charge in these resonance structures with a partial positive charge right next to it. And that's bad. That makes this all higher in energy than benzene by itself. Right? Benzene by itself doesn't have these partial plus charges at all, right? Because there's nothing substituted. So meta-directors are deactivating because we have these partial pluses everywhere in the molecule. Right, so it's less stable to form a full cation when you have an adjacent partial plus. So that's bad. So all of these resonance structures are higher in energy than benzene itself. All right, it's deactivating. But what's special about the meta pathway? Well, if you look at the para position, we have one resonance structure that is particularly bad. In this resonance structure here, right, we have a plus directly next to our partial plus, right? And that's pretty high in energy. We do not want to have two atoms that have both a positive and a partial positive charge right next to each other. And that's the same when you attack at the ortho position. So these resonance structures aren't extra stable, they're actually extra unstable. All right, they're extra unstable. Whereas if you look at the meta position, right, if you look at the meta, we've got our plus, and our plus, and we never have a positive charge on the atom that's directly attached to that partial positive charge, right? So it doesn't have these extra unstable structures where the plus is directly next to it, all right? So it's kind of like you have two paths, right? We can take the meta position or we can go the ortho-para way. So the meta position is not as stable as benzene, neither is the ortho-para, that's not as stable, but this is even less stable than that is, right? And the analogy I like to use is, okay, if you're, you're out for the day and you lose your wallet, right, or you lose money, right? Losing money is a bad thing, but with the meta director, you're only losing $10, or if you had the ortho para director, you just went to the bank and had $100, right? So if you have to lose money, you'd rather lose less, right? So you'd rather, you'd rather lose the $10 rather than the $100, right? So the meta directors are deactivating, right? The meta directors are deactivating, but the meta pathway is less unstable versus the ortho para, okay? Because these two structures here are particularly bad. Right, so I just want to add one other sort of structure here. If we look at something like this, let's take an NH3 with a plus. What type of director would this be? Right, so if we add some E plus here, what type of director would we have here? So in this example, right, we have a molecule that already has a plus, right? So we definitely don't want to have a plus here, right? So a partial plus is bad, a full plus is even worse. So anytime you have kind of a partial positive charge or even a full positive charge on here, right, that's always going to be a meta director. Right? So here this would again be a meta director because you want to avoid having a positive charge directly attached, avoid having a positive charge directly attached, and that would happen if it was ortho and para. So the meta director is basically the lesser of two evils.